Welcome everyone and thank you for joining us for our expert sessions. These are short webinars that take place every 2 weeks and last no more than 30 minutes, bringing you valuable insights from industry experts. Today, we are honored to have Sergio Panetta, Vice President of Engineering at I-Gard, as our speaker. Sergio holds a bachelor and master degree in engineering from McMaster University and brings over 30 years of experience in switchgear design, commissioning, troubleshooting, power system protection, and grounding. He is a senior member of IEEE, a member of IET, and consulting engineering recognized by PEO. As a leading voice in electrical safety, Sergio actively contributes to global standards. He chairs several industry working groups, including IEEE 3003, Grounding and Bonding, C5732A and P1584, and represents Canada in IEEE IEC committees, TC14 and TC64. His expertise extends to CSA, IEEE, IEC, and US safety practices, and he holds multiple US patents related to electrical safety. We are thrilled to have him here today and appreciate your participation. Let's get started.
Thank you, Andrea. Just want to make sure that, just check to see if you can see my screen. You should see the title, Neutral Grounding Resistor Sizing and the Importance of Coefficient of Resistivity. All right, so we're going to discuss resistance grounding and the importance of the coefficient of resistivity in resistance grounded systems. So system grounding, a resistance grounded system it's a grounding system basically. So instead of having a solidly grounded system, which I'm sure you're used to, where you take the neutral point of a transformer and ground it solidly to ground, we place a resistor in that path. By placing a resistor in that path from the neutral to ground, we have a resistance grounded system. Now, depending on the size of that resistor, you could either have a low resistance grounded system or a high resistance grounded system. So typically in 480 and 600 volts and medium voltage systems, we limit the ground fault current. All ground fault currents must return back to their source. And because of the resistor, it limits the ground fault current because the neutral will never elevate above line to neutral voltage with respect to ground. So the advantage of having a resistance grounded system is that there's no arcing ground faults as with solidly grounded system and no over voltages as with respect to ungrounded system. So it's got its advantages over solidly grounded systems and resistive grounded systems. For solidly grounded systems, you can run your system with a ground fault on it all the time. You should find where the fault is eventually and rectify it. And with an ungrounded system, if you want process continuity, you would put a resistor in there, not to increase process continuity, but to help you find the ground fault and clear it as quickly as possible. So selecting and installing a neutral grounding resistor. Obviously, the first thing I think any designer should do is determine what type of grounding system they have or they would like to have. Solidly grounded systems, and you look at all the pros and cons of a solidly grounded system. A resistance grounded system, look at all the pros and cons, and an ungrounded system. You can still choose to have an ungrounded system, but it is the first thing you should decide to do in any installation. So if you choose a resistance grounded system, you can choose between a high resistance grounded system or a low resistance grounded system. On a high resistance grounded system, NFPA 70E and CSA Z462 state that if you have a system that's less than 5 kV and less than 10 amps, then you have a high resistance grounded system and you have a arc flash mitigation technique. So why is it 10 amps? Because 10 amps is basically the resistive current is equal to 10 amps or less, and the resistive current should be greater than or equal to the charging current of the system, and that's defined as 3IC0. The advantage of that is you have faulty equipment can continue to run, scheduled downtimes, and lower repair costs. The resistor must be rated for continuous duty in this case, and allows faults to be located without de-energizing feeders. So you can actually look for a ground fault while everything is running. This means that you don't have to open up doors and introduce a hazard when you're looking for a ground fault. You can actually locate the presence of a ground fault or the location of a ground fault with the doors closed. So your electricians looking for the fault can do it in a safe manner. Overcurrent coordination is maintained, and selective second ground fault protection is available. With the low resistance grounding system, this is for systems that are greater than 5 kV or the charging current is greater than 10 amps. The disadvantage of a low resistance grounding system is that you have to trip on a ground fault because your current is greater than 10 amps. Now, on a solidly grounded system, you don't have ground fault protection unless your system is greater than 150 volts to ground and greater than 1,000 amps. So for a resistance grounded system at medium voltage, you have to trip even if the ground fault current is 400 amps. Ground fault currents are limited to between 25 and 400 amps, and the short time resistor is 10 seconds. So the resistor is in the circuit for 10 seconds, allowing you time to selectively determine where the ground fault is and isolate that faulted feeder only and keep everything else running. Now, we say 25 to 400 amps for a solidly grounded system. We've seen systems here that go up to 2,500 amps, 3,000 amps. But in some cases, we've seen systems at 25 amp or 10 amp, and they trip on the first fault for low resistance grounding systems. So it's sort of flexible. The thing you have to remember when you choose a low resistance grounding system is that you have to select a size of resistor to limit the fault current to something that your protective system can detect and isolate. There's no sense having a low resistance grounding system at 100 amps if your minimum ground fault protection is going to be 400 amps. So the factors in sizing a neutral grounding resistors, you have to select the rated voltage. The resistor shall be rated for continuous voltage where the rated voltage is equal to the line to neutral voltage of the system. So if you have a 600 volt system, the resistor must be rated for at least 347 volts. The current seen during the maximum ground fault is going to be a value equal to the voltage, which we've already determined at 347 volts for a 600 volt systems, or 277 for a 480 volt system, divided by the value of the resistor in ohms. So if you want your fault current to be limited to 10 amps on a 600 volt system, your resistor is going to be 34.7 ohms. 347 volts divided by 334.7 ohms is 10 amps. So that's how you select your resistor. And the only thing you need to worry about is that the resistive current, I, in here, is going to be greater than the capacitive charging current. Now we're going to talk about the capacitive charging current a little bit later, and it's something you can't really measure easily. Now you have to determine the time. So we've got the voltage, we've got the current. Now, how much time is your fault going to be on the system for? If it's a high resistance grounding system, that time is continuous. But you can have low resistance grounding systems where your time is limited to 10 seconds, 1 minute, 10 minutes, or even longer if you want. It's up to you. What that tells me as the manufacturer of the resistor is if you choose a 10 second, 1 minute, or 10 second resistor, I've got to make sure that the resistor element does not exceed what is dictated in CSA C22.2 number 295 or 67.32 in IEEE, and I believe there's a European standard, IEC 60076 Part 25, but they all have the same volt temperatures. For a continuous duty resistor, the element temperature cannot exceed 385 degrees C over ambient, according to CSA. This table's out of CSA. In IEEE, it's 375 degrees C Celsius over a 30-degree ambient, and so this one is IEEE, 385 over a 30-degree ambient, and for CSA, it's 375 degrees C over a 40-degree ambient. The extended time and 10-minute is 610 degrees Celsius, and the less than 10 minutes, so if you have a 10-second rated resistor, 760 degrees C ambient. So we talked about the system charging current. The system charging current is exactly that. If you have a fault on A phase, the current is going to flow through the capacitance of B phase and C phase. One misconception that I've come across a lot is that the capacitive current goes through the resistor. It does not go through the resistor. The capacitive charging current goes through the two unfaulted phases. And if you wanted to determine what the fault current is, in this particular case, if you take the fault current here on A phase, it is equal to the resistive current plus the capacitive charging current. So you can see that if the resistive current is 5 amps and your capacitive charging current is 5 amps, your maximum fault current is going to be 7.07 amps because you add them up vectorially. What that means when you're selecting a resistor is you have a temperature elevation of the resistor element, and the resistance of the resistor is going to change with the change in elevation of temperature. So the temperature coefficient of resistivity, alpha, is equal to the difference between the final resistance minus the initial resistance divided by the initial resistance times the change in temperature of the element. And you've seen that we can have 760 degrees C change in temperature. So if alpha is very, very small, the change in resistance becomes a major factor in the percentage change of the resistance at the end of the fault than at the beginning of the fault. And that's what we determine as the temperature coefficient of resistivity. And this is a special alloy property of the material you're using for the change in resistance or for the material. So CSA 295-15, which is being rewritten right now, the rated voltage test. The assembly shall be operated at a maximum line to neutral rated voltage. The current shall be measured immediately for a short time rated device right before the end of the time rating. So if your time rating is 10 seconds, at 9.9 seconds, you're going to measure the current. If the current varies from the initial current to the final current by more than 20%, it is not a CSA approved device. IEEE 32 says the same thing, but in a different way. They say the change in resistance shall not change by more than 67% from the initial value to the final value. When you choose that 34.7 ohm resistor, you've chosen what that resistor is going to be at an ambient temperature. At the end, for a continuously rated resistor, you know the temperature change is going to be maximum 385 degrees. So what does the final temperature become? And what does the final resistance become? And when you know what that is, you know what your final current is going to be. So this is important when we're looking at devices like case number 1. You have a 4160 volt system. Your line to neutral voltage is 2400 volts. Your rated current you want is 400 amps. Time is 10 seconds. So your maximum temperature rise for that 10-second resistor is 760 degrees C. Your resistance is 2400 volt divided by 400 amps, 6 ohms. And here are 4 examples of 4 different common elements that are used in the resistor industry. And here are the corresponding temperature coefficient of resistivities. And the units of this is 1 over degree C. So for AISI 304 stainless steel, 0.00092. For stainless steel 430, 0.00146. For 18SR, which is a common element used, 0.00358. And for 1JR, 0.000241. So you can see all of them look relatively low. These look like low values, but when you multiply by the 760 degrees C, the resistance changes from 6 ohms cold to 10.2 ohms at the end of the 10 seconds, or when it reaches 760 degrees C. This corresponds to a decrease in current from 400 amps to 235 amps. 430 changes, the resistance changes by 110%. So from 52 to, so 6 ohms to 12.65 ohms. So your resistance doubles. And we've all seen 430 stainless steel resistors. Now, people choose stainless steel resistors because they believe they're getting a better alloy, but you have to be careful about which stainless steel you're choosing. You should really dictate the maximum resistance change you would like to have in your system. And so you can see that these two fail the CSA test. And for high resistance grounding system, same 2 resistors change because their resistances increase from 55.4 ohms in a 277 volt 480 volt system, 5 amps, so it's 55.4 ohms. And the resistance has increased from 55.4 to 74.79, and the current decreased to 3.7 amps. The 430 changes from 5 amps to 3.2 amps, so you almost barely have a fault. It's just over 50%. But the 18SR and 1JR maintain within 10% of the resistance throughout the temperature range. So they are far better elements, and we use 1JR because it's a better element, and we give the user, our customers, the opportunity to have a more consistent current throughout the fault. Why this is important is because, for example, you have a utility transformer and you have reclosures. After the first or second reclosure time, the third one, the temperature of the resistor is going to be warmer. And when it is warmer, hotter, it may not give you the right amount of current for the next fault. So you may ride through it not believing there's a fault, depending on what you set your protection for. So we use it on Y-connected systems and delta-connected systems. So a Y-connected system, you can connect your resistor directly to the neutral point of the transformer. For delta-connected systems, you need to have an artificial neutral or some other means. In this case, we use a zigzag transformer. When you use a zigzag transformer on a continuously rated resistor, you have to have a continuously rated zigzag transformer. When you get to a low resistance grounding system and you have an artificial neutral like a zigzag transformer, the impedance of the zigzag transformer becomes very, very critical. because the impedance of the zigzag transformer plus the impedance of the resistor still has to add up to the impedance necessary to limit the fault current to the full value. The resistor should probably never be, should never be 55.4 ohms in a low resistance grounded system, because chances are your neutral for a 10-second rated resistor, the impedance of your neutral is going to add to the resistive neutral. And with that, thank you for spending time with me this morning. I know it's a lot to absorb, but if there are any questions.
Sergio, I have one question right here. It says, I saw most of NGR resistors are 5 amps and not 10 amps. When do we see 10 amps?
If you're a resistive current, where we use a lot of 10 amps is if there's a lot of capacitance in your network. So if you have a vast 600 volt or a vast 480 volt system, and you have multiple sources, you can have more than 10 amps in your fault current. The resistor itself, it depends on you whether you use a 5 amp or a 10 amp, but you must make sure that you check to make sure that the capacitive charging current is less than the resistive current. We do 10 amps at times. Not often, but mostly they are 5 amp, but we can do 10 amps at times.
Okay. Next question says, can we have neutral loads in HRG system?
Oh, you know what? That's a tricky question. Can you have neutral loads? There's okay, in US, no. You prohibited to have distributed neutral on a resistive grounded system. In Canada, much to my disbelief, you are allowed by code to have a resistive grounded system. Although I really don't think it's a good idea, because I think it's dangerous. And the difference is you have to trip on the currents of the first fault, right? Because that neutral point is going to elevate to 347 volts or 277 volts, but you can have a distributed neutral by code in Canada if you follow the Canadian Electrical Code. Second thing, you can have a distributed neutral in Canada if you're doing metering. If you look at section, I think 6-412 or 8-412, you can distribute your neutral to the metering PTs for metering purposes, but that neutral has to be insulated throughout the entire length. It can't touch ground, because if it touches ground, you actually have a solidly grounded system. So yes, by code, you're allowed to have a distributed neutral. Practically, I would not recommend it.
Okay, next question. When with zigzag transformers are used, we must count both the resistor and the zigzag transformer resistance when calculated the fault current.
Say that again.
When with zigzag transformers are used, we must count both the resistor and the zigzag transformer resistance when calculated the fault current.
Correct. Now let's look at the zigzag. The resistor, it's easy to calculate the resistance of the resistor in ohms, because you're purchasing a X ohm resistor. With a zigzag transformer, it's much harder to determine the amount of resistance you're going to have. And you have to get this from the manufacturer of the zig transformer or your neutral grounding resistor supplier, such as me. You have to calculate the X over R ratio and the impedance at test per phase of the zigzag transformer, and then you can calculate what the impedance is of that transformer, and then subtract the resistance, the impedance, not the X, but the R part, from the resistor to limit the fault current when you have a fault to the desired value. We can have another session on this later because it's going to take a while to explain it. But the impedance of the transformer, primarily when it comes to low resistance grounded systems, because IEEE states that you can limit the fault of a low resistance grounded system transformer to 3% of its rated value. So again, it's hard to explain without the pictures. We may have to have a discussion of that later on.
Okay. And could you speak further about charging current and how to calculate?
Oh, calculating the easiest thing to do with the charging current is give me your single line diagram and your cable schedule, and I can calculate. I have a spreadsheet where I put in all the information. Most of your cable is going to be, most of your capacitive charge is going to be the length of cables you have. So think of a conductor as really a capacitor, because you have the copper or aluminum conducting part, which is at one potential. You have ground, which is another potential, and you have the insulation of that cable between them. So this is two potentials isolated by an insulated medium. So you have a capacitor. But that capacitor is distributed throughout your entire facility. So, and that's why cable manufacturers give you the capacitance of your cable in capacitance or microfarads per 1,000 kilometers or per 1,000 feet or per kilometer, not thousands kilometers. So with that, we can calculate what the capacitive current is in your system. So you can realize if you had an ungrounded system here, we can actually put a fault on A phase to ground, and we can measure at the point of the fault only what the capacitive charging current is. If you have a fault on a resistive grounded system, you can measure the fault at the point of the fault, the current at the point of the fault, and the current through the resistor, and we can calculate what the charging current is because we have this formula. Capacitive charging current also exists on a solidly grounded system, although it doesn't really matter because when there's a fault, you're going to have a ton of current, and the neutral is never allowed to elevate. The reason why we look for the capacitive charging current is to limit the overvoltages of your system. So with a resistive grounded system, we guarantee that your voltage elevation of the unfaulted phases is only going to be at 173% of rated. So with respect to ground. So instead of having 347 volts with respect to ground, you're going to have 600 volts with respect to ground. On an ungrounded system, because there is no resistive charging current, there is no limit when you have intermittent arcing faults in your ground network or in your network. And most of the time you're going to have intermittent arcing faults repeatable is in a motor. So your escalation of voltages becomes unpredictable.
Okay. Well, I think that will be all of the questions for now. We still have plenty, but we don't have time.
Okay, so I think what we'll do is we'll probably post the questions on our website. Is that correct, Andrea?
Yes, yes. We will create some papers and with all of the questions that we received. And we will post it in our website and also social media like LinkedIn.
All right, thank you very much. Everybody enjoy your day.
Much.
You can post more questions, we'll answer them all. You can also send questions to, you can also send questions to support@i-gard.com.
And thank you everyone for joining us.